Okay, so share screen. Voila. Okay, so today we're going to finish off transformers very quickly, and then we'll talk about reinforcement learning. This will be our last lecture for this year. Okay, so transformers are used for, well, these days are used for pretty much everything. But originally they were used for language, and the original paper was attention is all you need. Which has now been cited over 100,000 times. So it's a pretty influential paper. So the way transformers start, you have words, word I. So it deals with words, sort of. So the first thing it does, so you might have a sentence, individual ones. So I equals 1 to n. N words in a sentence. The first thing you do is words are embedded in some vector v. So this is called, these are called tokens. And typically, at least in the original paper, they were 512 dimensional. And the token was combined with position information. So P is position information, coded in kind of a weird way. Details aren't so important. So this was position in the sentence. Words came in order. And this was basically some x. So xi, so the set of words I equals 1 to 10 in terms of vectors, I equals 1 to 10. Okay. And these vectors were then turned into a new vector. We'll give the superscript h for head. So call it O I H equals the sum on J W. This is the matrix IJ. Call it H dot XJ. So this would be kind of a standard feed-forward network. Then you pass it through nonlinearity. What the transformers added to this was E was basically a softmax. E to the minus to the XJ dot gamma H dot xi divided by sum on M of E to the xm dot gamma H dot xi. So this has as a function of J. So this thing we can think of as, just AJ, and the sum J equals 1 to actually n, number of words of AJ equals 1. So this is really a probability distribution. And this gamma H, so gamma H was actually written as 2 vectors W KH transpose dot W KQ and WKQ dot, so then XJ dot gamma H dot XI is equal to because that's transposed, it's X J dot W KQ there, HQ WHK dot W. Actually, let's try this the other way around. W HK dot XJ dot WHQ dot XI. Okay, and this is called, oops. This is a query, and this is a key. So these names I never found them very illuminating. When once you know this is quadratic nonlinearity, that's really the key to transform. Okay. And then basically compute, so the way these things work is step 1, compute O H equals 1 to H. So these are called heads. And then 2, pass O I H equals 1 to H through a feed-forward network. Just standard deep network, and then repeat. So repeat a bunch of times, and at the end you get something that you can do whatever you want with. You can use it for translation or next word prediction. And large language models are right now trained on next word prediction, and that's all they're trained on. They're basically trained on autocomplete, and yet they do insanely well. And nobody really knows why. It's probably because language is slightly simpler than we think. Okay, so that's just sort of, so transformers are just another network, nothing special about them. They just happen to have this nonlinearity here. And the way it works is basically these terms here, these weight matrices here, allow each particular word, so a particular word here, so word I here is now, there's sort of an intentional mechanism that makes it pay attention to different words in the sentence, which is kind of what language works more or less. You sort of focus on, you kind of pair words. At least that's a hand waving explanation. Again, the fact that these things work is really a statement more about language. Okay, so that's it for DeepNet for sort of or supervised and unsupervised learning from data. I'm going to switch gears now and talk about a very important and probably the most successful learning field in neuroscience, which is reinforcement learning. Which is basically learning to act which is really learning to act based only on rewards. Okay, so the reward signal is a very weak signal, right? If somebody, says, give you an image and tells you what's in it, that's a lot more information than you do some action and you get rewarded or not rewarded. In a sense, everything is reinforcement learning, right? This is how species evolved. The reward was having more kids, and it was kind of a random search. And because the reward signal is not a very information-rich signal, in reinforcement learning, there's a lot of kind of random searching, try this, try that, see what works, and then figure out how to maximize reward. So we're going to look today, we're going to basically define the problem. Or define the standard setup. And really, RL divides the world into states, actions, and rewards. Pretty much the whole story. And basically, in some sense, reinforcement learning is a set of algorithms for maximizing reward. We'll start off with the TD, called temporal difference. Which is basically the cornerstone of reinforcement learning, especially reinforcement learning in the brain. We'll look at a few other algorithms. E-learning, policy gradient methods. I think that maybe some other ones. And then we'll consider specific. The decision making and time pressure. And I'll tell you sort of exactly what that is. Let me get. So that's it. That's the plan for today. So let's start with sort of the standard setup for reinforcement learning. So the world consists of states. So there are states. Which we call S, actions. Which we call A, and rewards. Use for what that means are. And there's a policy. A policy, which is sort of the key to reinforcement learning, is written in several ways. It's basically policy as the action you take. These actions are often probabilistic. So probability action given state. It can be deterministic, right? We sometimes write as P pi of A given S, or just P of A given S. So all these things are used for policy. So P is a probability distribution. P and pi It's kind of confusing. So P is probability distribution. And pi stands for policy. Okay. Okay. So sort of the simplest version of RL, the states can be continuous, right? It can be, in fact, in sort of the most general case, states are continuous, but in simplest version of RL, states are discrete. So simplest version. States are discrete. Okay. So you might have, so this is state one. This is state one. And I'll give a specific example of these later on. This is state two. But we sort of imagine this is state three. This is state four. And your policy is which state you go to next. So policy is really, so to speak, policy is sort of simple. Policy is which state you go to next. Sometimes okay. Collect a reward. So let's say we go from state one to state two. Get an R. Let's say S1 to S2. You collect a reward. But the constraints is say this is R. S2, S1. Okay. And you can sometimes go back. I mean, not all state transitions are probable. There's some things you can't do. And so what's important is, so states have sort of key to reinforcement is that states have values. So states have value. So I with my pen. Oh, my pen. No, we don't have pen problems again. So states have value. And so the key thing is that when you basically the value of a state is when you go from state one to state two, you collect a reward. So let's say this was equal to 20. Okay. Going from state one to state two, you got a reward of 20. So if the value here, the value of this state, d equals 80, the value of this state would be v equals 100. Okay, because basically, if this state is worth 80, then this state must be worth 100 because you can collect a reward of 20 from going to one state. So in general, so loosely, this is sort of approximate v, the value of the state to the value of state one equals the reward you get from going to state one to state two, and then plus the value of state two. Okay. Now, that obviously is going to be a little bit strange if there are loops. And we're going to fix that in a second. So if suppose, for instance, that R of S2 to S1 equals 10, right? So in that case, if the value of state 1 was 100, the value of state 2 would be, looks like it would be 90. So to fix that, we had a discount factor. Okay. So this is the key idea, but it's kind of an approximate statement. So gamma is discount factor. See how this comes in a second. So 0 is less than, gamma is less than or equal to 1. There's no discount at all. Actually, it can't really be 1. Less than 1. Listen, so between 0 and 1. It's an approximate statement because really the value of a state, let's be more little more clear here. The value of a state equals discounted sum of total future reward. And the fact is total future reward is what makes things hard. So for instance, the value of one way to think about this is that the value under some policy, and the value depends on the policy, right? Because the future reward depends on what you do. The value under some of the state equals R, the reward you're getting from going from S to S prime, or S to S1. Go with S prime. Plus gamma. We're just going to look at rewards. Reward from S prime, S double prime, plus gamma, R of S double prime, S triple prime, gamma squared, because it's more in the future, plus gamma cubed, R of S triple prime to S154, plus dot, dot, dot. And we can write this as plus gamma R of S prime to S double prime, plus gamma R S double prime to S triple prime, plus gamma squared R of S triple prime to S154, plus dot, dot, dot. And you'll notice that this term here is just value of state S prime. Okay. Under policy pi. You change your policy, you change what you do, and you get different rewards. And so we could write then sort of the fundamental equation for in reinforcement learning equals R, which I wrote down earlier, S to S prime, plus gamma R, that's gamma V, gamma V pi, that's prime. So let's be clear about this. This quantity here, the reward you get from S prime So this is a property of the world. You have very little control over that. Okay. It's also really stochastic. I mean, we wrote it deterministic and stochastic, so it's really big. So that's comment number one. So you have control over the policy, but not over the world. Okay. And the other thing is, so this is for deterministic setting. The real story is that we can write the actual story. So this is now, so in the realistic setting, which is stochastic, is basically under policy. There's actually, under policy, there's all the probability distribution going. So V pi of S equals the sum on S prime, probability of under some policy, which means some action of going from state S to S prime, times the reward you collect when you're going from S to S prime, plus the plus the reward you get starting at S prime and going to somewhere else. So gamma, again, gamma. Now the sum on S double prime of P pi of going from S prime, S double prime, times reward and so on. Reward you get from S prime to S double prime. Let's close brackets. But of course, this quantity here is just V pi of S prime. So again, we get sort of the real story. Is it V pi of S equals the sum on S prime, P pi of S goes to S prime, times R of S goes to S prime, plus gamma P pi of S. So this is almost Bellman's equation. So under policy, that tells you how to, if you know these probabilities, so if you know the probabilities, this is just a linear equation for the values in terms of all the rewards. If you know all the rewards, you know the probabilities, it's just a linear equation you can solve. Which is kind of easy, but the reason things get complicated is the goal is to maximize reward. So this is, if you knew your policy, let's put the pi here. Oops. So if you know your policy, you know exactly what to do. So basically what you want to do, so this is if you know your policy. If you know the policy, you can find the rewards. But Bellman's equation is basically tells you what so what the policy should be. So basically V Oops. So v pi of s equals max over actions of the sum on s prime p of s prime goes to s given the action times r s goes to s prime. Reward you get. Oh no. Oh no. Shot at the shared window screens. Man, this is irritating. Okay. We lost that, but I will put it back into the it has not been behaving. Let me see. Recent. Yeah, I didn't say it. Okay. I will put it back into the lecture notes. Oops. Share screen. Okay. I'll put this back in lecture notes. But right now we'll just start with Bellman's equation. And hope this doesn't crash again. So v pi of s equals max over all possible actions of the sum on s prime, probability of s goes to s prime given action times r you get when you go from s to s prime, which may be action dependent, plus gamma p pi of s prime. So this max operation, so this makes things complicated. Things hard. So you have to choose the operation that maximizes future rewards. Okay, and that can be, I mean, and it's really the maximizing future rewards that makes things hard. If gamma were 0, so gamma equals 0, life is easy. And if you ever hung around little kids, their gamma is basically close to 0 because you just choose the action to maximize your reward. Okay, so let's say you had, this is state 1, this is state 2, this is state 3. So let's say this is state 4. And let's say if you went this way, you get, R equals 100. If you go this way, R equals 10. Let's go this way, R equals 100 again. If you go this way, R equals 1,000. Okay. So the value of this state under no discounting, right? The optimal thing to do is to go in this direction. The optimal thing to do is to go this way and this way, right? Your reward's going to be 1,010. But if you're greedy, so the greedy policy, so this is a greedy policy. That's greedy, okay? And if the discount factor is small enough, that would make sense, right? Because the future rewards are massively discounted. But a sort of a reasonable discount factor close to 1, you want to take the non-greedy policy, and that requires looking ahead. Okay, and that's really why reinforcement learning is so hard. In general, it's hard to predict the future. Okay, it's hard to look ahead and figure out what's going to go on. You have to do a lot of planning. So, so that's the basic theory and reinforcement learning. So, performing this max operation is hard. Reinforcement learning consists of tons and tons of algorithms for finding the optimal policy. I'm going to start off with sort of the simplest one. If we go back to sort of a naive version, let's say you have some world and you're just wandering around. Okay, so you take some action, you get your choice of action. Sometimes you may not have all actions are possible, but every time you do some action, you collect a reward. Okay, and let's say we have a set of states. Let's say we know what they are: S1, S2. Say they're in states. Give a value to each state. Pretty much a random value to every state. Each state. Okay. So we have V of S. Wander around state space, taking actions. And wander around state space. Okay. And remember, our sort of fundamental equation is value of a state equals reward going from state S to S prime plus discounted value of state. Okay. So this is going to be our fundamental equation. Copy that. Copy that to the next page. This page. Save this every now. Copy that to the next page. And so remember, we've assigned a value to every state. So the reward we expect, let me go, state S to state S prime is gamma. So expected reward. So R expected is equal gamma V of S prime minus V of S. Okay. Sort of the difference in the value. Remember, gamma is usually close to 1. Okay. Expected reward is gamma V of S prime minus V of S, and the actual, so the error, which is called the RPE, equals reward, prediction error, equals the actual reward. You get the sign, right? The reward you get from when you go from state S to S prime minus gamma. Actually, I got this backwards, didn't I? The reward is it's V of S minus gamma V of S. And gamma is close to 1. So it's V of S minus gamma V of S prime. And that is reward that prediction error, what you get relative to what you expect. Humans and animals are very sensitive to this. And in fact, sort of in the old days, it's still kind of true. This is signaled by dopamine. Okay? So if you get more reward than you're expecting, you get a shot of dopamine and you're happy. If you get less reward than you're expecting, you get less dopamine than you expect and you're not unhappy. And this is actually observed in the brain. Very, very famous set of experiments. Tell you about it now. Paranoid about losing this. This is Schultz. Diane. And Montague. Came out of Science in 1976. At least some of these people almost feel sure will get the Nobel Prize. Schultz and Diane recently got the Brain Prize, which I think is worth about $1 million. Reed Montague did not get it. So here's the experiment. The experiment that Schultz had done, that they were modeling. And the experiment was done was not clear what was going on. So monkey, there's a fairly common paradigm in behavior. It's conditioning, Pavlovian conditioning, instrumental conditioning. Yeah, monkey gets a CS. What's called the CS. Names are horrible. Condition stimuli. We just think of it in tone. And then about 1 second later, 1 second later, gets a reward, juice reward. And basically, and they recorded it from dopamine neurons. So if you plot, what we're going to plot is, so this is time on this axis. So this is when the tone occurred. This is when the reward occurred. Separated by about 1 second. And what we're going to plot is, we're going to plot dopamine response. So, well, so Schultz recorded from dopamine neurons in monkey. And on trial one, basically dopamine, the firing rate of neurons, so this is dopamine response, was pretty much it's pretty much flat. Actually, let's draw some dashed lines here so we know what these are. So here's the time of the tone, the time of the reward. Okay. The dopamine response was pretty much flat. The tone, the animal didn't know that tone meant anything. Gets a drop of juice and big burst of dopamine. Firing rate goes up. Okay. Dopamine neurons active. Okay. Because it's an unexpected reward. Okay, this is trial 1. By the time we get to trial 10, okay, now the animal has sort of learned that this reward, this tone, so it's sort of not clear whether there's a sudden jump. And this is probably trials average over different monkeys, but the sort of the story is, you get the tone is now surprising, right? The tone is now the monkey's learning that tone is predicting dopamine, and by the time you get to trial 100, not actually sure about the numbers, maybe sooner, the tone has no effect in the monkey. Sorry. Trial 100, the tone occurs, big shot of dopamine, the reward occurs, and nothing happens. Okay? That's because it's completely predicted. The animal knows absolutely for sure it's going to get a reward. The happiness comes when the tone occurs. And if you actually, if you don't provide any reward, so this is no reward, no juice, sorry. Now the reward prediction error is negative. The monkey is expecting something and doesn't get it. So this is actually, when I heard this, a lot of things like this is super important in life. So especially if you have kids or a significant other, so kids are especially bad. Never ever go into a store and buy a kid present, because what happens after a while, walk in a store, they get a shot of dopamine because they know they're going to get a present, and when they don't get a present, they cry. Okay, they always need to be surprised. Never go on a trip if you eventually have kids, you go on trips, you come home, don't consistently buy your kid a present, because after a while they expect it, they get no happiness from it, right? You get a shot of dopamine knowing that you need. Okay, so people have to be surprised. This is true of significant others. Don't be consistent with rewards, because then basically they'll have some predictor of rewards and the rewards won't be. Okay. So you can actually, so this is, and so you can learn, so you can use this reward prediction error actually. Let's put it on this line. So we'll go in order. So we can use the RPE to learn. Okay. The reason you get a shot of dopamine is because it's a learning signal. So you can update the value so you have in your book. Remember, initially we assigned random values to all the states, but now we can update these values by the reward prediction area. So the change in estimate of the value equals eta times R of S goes to S prime minus V of S minus gamma V of S prime. Okay. So if the reward is higher than you expected, so this does what it says: reward higher than expected. increase value, increase your estimate of value. And the reward lower than the expected, unexpected. Decrease value. Okay, that's what was happening here, right? Initially, eventually, the tone predicted a reward. Completed, the tone was completely unexpected. You get it, and so the value goes up. And eventually the tone becomes value. Okay, so this is, and so this is gives you the value of every state, but it's not, doesn't, and then so what you do is you figure out how to go to stage like that. Okay. The problem, of course, is it doesn't really link actions to states. You have to kind of figure that out. And what's sort of more common for these kind of problems is something called Q learning. So instead of value learning, so V value, remember, so V of S equals total, pi there, total feature reward. Reward, total feature, discounted reward. Under some policy. So there's also something called Q learn. There's a key value, which is more useful. So Q under some policy of S comma A equals total future reward, total future discounted reward. Reward under some policy given action A. And that, of course, is really much more useful, right? Because it tells you what actions to take. And so basically, we can write down the Q as before. We can write the value of Q under some policy equals R of S going to S prime given A. In fact, it's probabilistic plus gamma V of S prime, and V of S prime is max over A. Okay. So the value of state is still so the best you can do. The Q policies give you sort of a lot more information. If you know the Q value of every state, you know exactly what to do. As you can learn as before with you can update Q based on the prediction error or prediction error. But now you have to have a policy. So given Q values, what's your policy? So if you knew Q values perfectly, the policy would be A equals max over A prime of Q as given. Just basically pick the optimal action. Okay. But of course, there are two problems with that. First of all, you never know Q values perfectly. Second of all, the world changes. So more typical A would be, you might do max the best policy of Q of S given A prime with probability 1 minus epsilon, and then random A with probability epsilon. So this is called epsilon greedy. Or you might, or the other one is softmax, where basically P of A, in state S, equals E to the beta Q of S. S comma A, S, this should be S. What notation did I use? Should be S comma A. So S comma A. S comma A over the sum on A prime of E to the beta Q of S comma A prime. So this adds up to 1, and so beta equals infinity is basically deterministic. You pick the best, and then beta equals 0 is random. So typically when you're running, when you're doing a task, you start off with beta kind of low, because you don't know what's going on, and then you get more and more sure you beta. Same thing with epsilon greedy. You start with small epsilon and slowly increase. Okay, so let's take a break. When I come back, I'll talk about two more policies, two more algorithms, and then we'll switch to a particular system. Okay. Okay, so back in 5 minutes. Okay. So I'm back. Let's talk about sort of two other methods for learning policies. One is deep RL. Doesn't really have to be deep, but it typically is deep RL. Often deep Q learning. So basically in this, you parameterize the policy with some set of parameters theta. So your policy looks like P theta of action given state. Okay. It's important it's a probabilistic policy for this to work. And what you want to maximize, so maximize infinity or S. Maximize very abstractly integral d tau r of tau p of tau. So tau is a trajectory through state space. State space. And basically it can be written P of S0, P of A given S0, P of S1 given S0 comma A, P of A given S1, and then so on until the end. Okay, and we maximize it by taking a derivative. So we update our basic state equals eta partial of respect to theta of integral d tau r of tau, and then times this quantity here. Okay. Now the partial, so we're going to use what we can use is the partial. We take a derivative, it's basically all these products, and the partial of theta these things are parameters by theta, right? Of this long string, so we can write this as sum on S of, actually let's go to sum on K of this long string times the partial of P theta of A given SK with respect to theta divided by P theta of A given SK. Okay. It's just basically, it comes from the fact that dx of A times B times f of x times C equals, A times B times f prime of x times C equals A times B times f of x times C times f prime of x divided by f of x. We're just going to use that over and over. Okay. And what that means is that save this. Delta theta equals eta times sort of integral d tau r of tau p of tau times the sum on k partial of log p theta of A given Sk with respect to theta. Okay. And so P theta be parameterized by a deep network. And the way we do this is we just the way we do the integral is we just sample. So we, have some, we start with some policy, we, have a policy. Okay. And then just, perform the task for a while. Task, collect rewards. And then update by delta W, delta theta equals, rewards we've collected. We collected. Some factor there times the sum on K. Just take all these through. Divided by theta. Okay. And this underlies a lot of deep learning algorithms that went off at the same time as parameterizes the policy, parameterize the values, the Q values. But it's actually, it's kind of nice because you don't have to know much about the world. Just parameterize with this deep network. They're powerful and expressive. It can be slow, but it generally works. Sometimes you have to tweak a little bit, but it's not a bad idea. And finally, we've really been focused on Q values. So in some sense, all of this was more or less model free. Okay. So model free means we didn't really have a model of the environment. We just, collecting rewards, looking at values, taking actions. But in reality, in model-based, instead of focusing on values, you learn transition functions. Right. Basically, you learn probability of S goes to S prime given an action. Okay. And you learn that for, and so it's maybe not obviously clear why, taking action, the world is probabilistic. The state transition probability would be probabilistic. It's actually very common. And that's because the world is hard to predict. So you do some action, you don't really ever know exactly what's going to happen. A really simple example is, catch a train. So you want to catch a train. So leave your house at leave house at 8:05. P of catching train, or catching the train you want, let's say equals 0.9. Leave house at 8:10. So leave house at 8:10. So P of catching train might now go into 0.4. Okay. So you have to trade off the how badly you want to catch a train. Maybe you want to leave at 8 o'clock, make it look high. Maybe not so worried. But the point is that these state action transitions are always probabilistic, or almost always. Sometimes their probabilities are high, sometimes not. So basically, if you sort of know all these state transition probabilities, it's kind of useful, right? If you know this is S1, S2. If you know P of, S1, S2, given an action, if you know all these probabilities, now it's quite powerful. First of all, if you also know the rewards, you can actually work out the optimal policy, do some planning, and we do a lot of that, right? There's a lot of, you have a model of the world. It's certainly true for navigating. You want to get from one place to another, you sort of map ahead, do it. But it shows up all the time. And model-based is planning. It involves a planning. Then model 3, we just model Q values, modeling habits. And humans use a mix of the two. Often you start off planning, eventually turn into habits, because planning is hard. You don't want to have to plan every time. So you kind of want to go back and forth between the two. Okay, so that's all been theory. What I want to do now is pick a particular example, which on the surface is going to seem kind of artificial, but in fact it's an example used a lot in animal experiments. Decision making under time pressure. I mean, it's nice because sort of the state and action space is kind of simple, but it still has a lot of the features of reinforcement learning. So it's just, I'll call it the coin flip problem. Okay, so I have two coins, called 1 and 2, and the probability of heads given coin K, say, equals PK. Okay. So here's the problem. So I randomly choose a coin. Okay. I start flipping it. And I tell you the sequence of heads and tails here. Heads, tails, tails. So you tell me which coin I picked. And the reward, let's say, equals +1 if correct, and minus rho if wrong. Okay. So the problem is, when do you make a decision? Make a decision. And the trade-offs are kind of obvious, right? Let's say P1. It sort of depends on how close the probabilities are, but the more coin flips you observe, the more likely you are to be correct, but there's a cost of time. Okay. So this is our setup, and our goal. The goal is going to be, so our goal, maximize. So we could use discounted reward, but reward P in a time, which is sort of another way to discount. So the idea is we're playing this game over and over again, and really discounting doesn't make a lot of sense unless you play it for years and years. So we just say, okay, one max range reward P in a time. So the goal is to maximize. So basically, we play the game over and over again. Play the game over and over again. So maximize the sum on I of Ri over the sum on I of Ti. So Ti is number of coin flips in game I. And Ri equals reward in game I. Okay. So this is kind of nice. There are two actions. Make a decision. So one is gather more evidence. And two is you make a decision. Okay. So this actually game has two interesting features. One is the fact that we're doing average reward reinforcement learning, so we want to maximize reward time. And the other is it's not actually completely clear what we mean by state. Okay. And so for the first one, we're going to write down sort of a usual equation. So the value, I'm going to be abstract about the value of the state. The value of the state so the value of a state, we won't say what a state is, we're going to work that out in a second, equals, let's say we keep collecting information. We get V of S prime, our new state, or we get reward. All right, some average reward is a function of S prime. Yes. So this is make a decision. Say, okay, we think it's coin 2. And this is basically, if you're doing nothing, it's collect more information. In this case, though, you actually, because we're doing average reward reinforcement, we want to subtract off something. Actually, we can't be rho anymore. Let's see. C is a cost of time. Okay. So basically, we're going to work out what C is in a second. If you collect more information, it costs. So the value is the value of your future reward and C. And so what this means is that basically a reward in task I is going to equal R bar of S of, it's R bar, whatever reward we get in that task S minus C T in task I. Okay. So if we need to set C equals average reward. So what we have to do is sort of update C on the run, because basically our total reward, if we do this, remember R for lots of tasks, I equals 1 to N is going to be the sum on I of Ri bar minus C, the sum on I of Ti bar. And that implies that C equals the sum on I of Ri bar over the sum on I of Ti. It's just Ti, not Ti. Okay. So it's kind of, reinforcement learning is full of tricks. This is one of them. You do average reward reinforcement learning. So we basically update C on the fly. And so it kind of makes sense, though. There should be a cost of collecting more reward, and the cost is the average reward. So this is the global average reward rate. So that's a little bit of a detail. What I want to talk about now in the last few minutes is what do we mean by a state? And so this is kind of important. So the state, whatever the state is, must have sufficient information to compute reward. Okay, whatever the state is, right? So it's state. Remember, we need to collect a reward for going with state 1 and state 2. We have to be able to know what that reward is. Okay, so how do we do that? So basically, we need to know the probability of so to know the average reward, if you go back to this, basically here, so these are two possibilities for reward. We have to know the probability of being correct. In some sense, everything depends on that. So we know what probability of which coin it is. So there are only 2 coins. So let's say, so probability that it's coin 1. So P of coin 1 given a sequence of flips, call it X1, X2, Xn. So X equals heads or tails. That's what we want to know, equals by Bayes' theorem, probability of X1, X2, Xn given C1, P of C1 divided by P of X1, Xn. Okay. And this, the term on the top, because things are independent, X1, Xn equals a product, I equals 1 to n of P of Xi, given that's going 1. Given. And then oops. And this is basically equal to P of heads given coin 1, the number of heads, times P of tails given coin 1 times the number of tails. This is number of heads. And this is number of tails. Okay. And we're going to take log of that. So log P of X1, Xn given C1 equals NH log P of heads given coin 1 plus NT log P of heads given, sorry, tails given coin 1. Okay. And what we really want to know is, so we want to know which coin is most probable, so we want the ratio of log probability ratio. Actually, well, not yet. So ratio is important. P of log, we want log of the ratio. Oops. P of C1 given X1, Xn over P of C2 given X1. And that's basically NH number of heads times log P of heads given coin 1 divided by P of heads given coin 2 plus n tails log P of tails given coin 1 divided by tails given coin 2 There's also plus the prior log P of C1 over P of C2. Okay. So basically, we're going to call this thing E on trial N equals evidence. Okay. So let's go. How much time do I have? I'm running out. Almost done. So evidence on trial N equals NH log P of heads given coin 1 over P of heads given coin 2 plus NT log P of tails given coin 1 over P of tails given coin 2. Okay. And the nice thing is evidence is easy to update. Sorry. Right. If you get heads, so heads, EN goes to EN plus log P of heads given coin 1 for P of heads given coin 2. And you get tails, EN goes to EN plus log P of heads given, P of tails given coin 1, but P of tails given. Okay. So the policy is now quite nice. Policy, you put E on this axis, and you just coin flips. Then you sort of go up. Oops. You start here and you go up, down, down, up eventually. So the policy is make a decision. So the state is really this. So this is now becomes a state. So this is kind of the case where, in some sense, there was an internal hidden state that we had to infer from data, which is quite common. And this is codes for a drift. These are basically called drift diffusion models. I could talk for days on these. A big thing in neuroscience, people actually did experiments where animals had to play effectively the coin flip game, and they look in the brain. They actually find areas that seem to be accumulating. Okay, so I'm out of time. I'm going to stop now. As usual, these will be online shortly. And I'm going to fill in the missing lecture. Yeah, it's saved. Oops. Okay. So if you have any questions, feel free to email me. And like I say, this was the last of my lectures. Okay, bye everybody.